Welcome to this video on solving the classic coding problem, word search, from LeetCode. In this problem, we're tasked with finding if a given word can be constructed by traversing adjacent cells in a grid. We'll break down the problem, explore some approaches, and walk you through the solution step by step. Let's get started. In this problem, you are given a two-dimensional grid, or board, consisting of m rows and n columns, where each cell contains a single uppercase letter. Along with this grid, you are given a string called word, and your task is to determine whether this word can be formed by sequentially connecting adjacent cells in the grid. Adjacent cells are those that are directly next to each other, either horizontally or vertically. It's important to note that a single cell cannot be used more than once when constructing the word. For the input format, you'll receive the board as a list of lists of characters, and the word as a string. The output should be either true if it's possible to form the word, or false otherwise. Let's explore this further with examples. In the first example, the board is a 3x4 grid, and the word we need to find is apt. The output here is true because we can construct the word by starting with the letter in the top left corner at position board 0, 0. From there, we move right to be at board 0, 1, then to C at board 0, 2. Next, we proceed downward to another C at board 1, 2, then to E at board 1, 1, and finally to D at board 2, 1. Each step follows the rule of moving to an adjacent cell, and no cell is reused, so the word is successfully formed. Now, in the second example, the board remains the same, but the word to find is C. The output here is also true because the word can be constructed by starting at the S located at board 2, 1. From there, we move right to E at board 2, 2, and then upward to another E at board 1, 2. Once again, all movements follow the adjacency rule, and no cell is reused, so the word is valid. Let's look at another example to understand when forming the word becomes impossible. In the third example, the word to find is ABCB. Here, the output is false. The problem arises because, while we can construct the sequence ABC using cells board 0, 0, board 0, 1, and board 0, 2, we cannot add another B without reusing the cell at board 0, 1. Since cell reuse is not allowed, it's impossible to form the word under the given rules. This illustrates how the constraints of the problem can prevent certain words from being constructed. Finally, let's consider some edge cases that you might encounter. First, if the word is a single character, you simply check whether that character exists in the board. If it does, return true, otherwise return false. Second, if the length of the word exceeds the total number of cells in the grid, you can immediately return false because it's impossible to fit the word. Third, if the word contains duplicate letters, ensure that the solution does not reuse the same cell multiple times to account for those duplicates. Fourth, if the entire board is filled with the same letter, verify that the word can still be constructed while respecting the rules. Lastly, if the board is one-dimensional, either a single row or a single column, make sure your approach handles these cases correctly. These scenarios emphasize the importance of designing a robust solution that accounts for all possible variations. To approach the word search problem, we first consider the brute force method. The intuition here is straightforward. From every cell in the grid, perform a depth-first search to explore all possible paths in the four directions up, down, left, and right. If any of these paths forms the given word, we return true. While this method is conceptually simple and ensures that all possibilities are covered, it comes at a steep computational cost. The time complexity is m n 4 to the power of L, where m and n represent the grid dimensions, and L is the length of the word. This exponential factor arises because, at each step, we explore four possible directions. Space-wise, it requires L for the recursion stack. However, the trade-offs are significant. While easy to understand, this approach becomes impractical for larger grids or longer words due to the sheer number of paths that need to be examined. To address these inefficiencies, we turn to an optimized depth-first search with backtracking. In the optimized DFS approach, we refine the brute force method by introducing backtracking. The core idea is to avoid redundant computations by pruning paths that cannot possibly form the word. When we visit a cell, we mark it as visited, often by temporarily modifying the board. Then, we recursively search for the next character in the word. If the current path does not succeed, we revert the cell to its original state so other paths can explore it. This approach is bolstered by key observations. First, once a path fails, continuing from that starting point will not work. Second, the grid itself can be leveraged to track visited cells, negating the need for additional data structures. And third, pruning paths early when a mismatch is detected saves a significant amount of computation. While the theoretical time complexity remains O(m times n times 4 to the power of L, pruning results in much better performance in practice. The space complexity remains O(L) due to the recursion stack. Despite its efficiency, this method may still struggle with very large grids or words. For variations of the problem involving multiple words, a tree-based approach could be considered. By pre-processing words into a tree, we can limit the search to paths that match valid prefixes. However, building the tree requires extra memory, and this method is unnecessary when only one word is involved. Based on these considerations, the optimized DFS approach with backtracking emerges as the most suitable solution for this problem. It strikes the right balance between simplicity and performance, leveraging pruning to eliminate redundant searches. While not the fastest for all edge cases, it scales well within the problem's constraints and avoids the overhead of additional data structures like tries, which are unnecessary for solving a single word search. The implementation is clear and efficient, making it a robust choice for this problem. The key idea is to recursively search for the word while marking cells as visited during exploration and reverting them afterward to allow other paths to use those cells. This ensures that the algorithm remains efficient and easy to understand. Here, the implementation of the optimized DFS approach begins by defining the recursive DFS function that handles the core logic. The function takes the current row, column, and the index of the character in the word being searched. If the index equals the word's length, it means the word has been successfully found, and we return true. Otherwise, we check boundary conditions and whether the current cell matches the required character. If not, we return false. When a match is found, we temporarily mark the cell as visited by modifying its value, then recursively call DFS for all four directions: down, up, right, and left. If any of these calls return true, the word exists. After exploring, we revert the cell to its original value to backtrack. Finally, we iterate through every cell in the grid, calling the DFS function to start the search. If a valid path is found, we return true, otherwise, false is returned after all possibilities are exhausted. This implementation ensures an efficient and clear solution to the problem. The problem we're tackling is to determine if a given word exists in an MXN grid of characters. To form this word, we can only connect sequentially adjacent cells, and adjacency here means horizontal or vertical neighbors. Importantly, the same cell cannot be used more than once while constructing the word. To solve this, we'll break the solution into a series of steps. First, we parse the input by reading the grid dimensions and the target word. We handle edge cases early, for example, if the grid or word is empty, or if the word's length exceeds the total number of cells in the grid, we can immediately return false. Next, we define a recursive search function, DFS, which will help us explore paths in the grid. This function has two key base cases. If the index reaches the end of the word, we return true since we've matched all characters. On the other hand, if the current position is out of bounds, already visited, or doesn't match the current character in the word, we return false. Then, during the search, we'll mark the current cell as visited by temporarily modifying its value. This prevents us from revisiting it during the same path exploration. Once a cell is marked as visited, we explore all possible directions: right, down, left, and up. To simplify this, we use a list of directional offsets, which allows us to easily compute the next cell's coordinates. For each direction, we recursively call the DFS function, continuing the search. After exploring all directions, we restore the original value of the cell so that it can be used in other potential paths. With our search logic in place, we then iterate through every cell in the grid. If a cell matches the first character of the target word, we initiate a DFS starting from that cell. If any of these DFS calls returns true, it means the word has been found, and we can return true immediately. If no path matches the word, we return false. The key insight here is in the use of backtracking. By marking cells as visited during the current path and unmarking them afterward, we avoid using the same cell multiple times in one path while still allowing it to be part of other paths. This ensures we explore all possible combinations efficiently. Another important optimization is early exit. If the remaining length of the word exceeds the number of unvisited cells left in the grid, we can skip further exploration for efficiency. Additionally, pruning the search as soon as a mismatch occurs helps reduce unnecessary recursion. For data structures, the grid itself is used to store characters and track visited cells during the depth-first search. A fixed list of directional offsets simplifies movement in all four directions. Now let's analyze the complexity. The time complexity is O, m times n times 4 to the power of L, where m and n are the grid dimensions, and L is the word length. For each cell, we explore up to 4 directions recursively up to L levels deep. The space complexity is O, L, as we use the recursion stack for backtracking, with a maximum depth equal to the word length. To illustrate, consider the example grid shown, where we have a 3x4 grid of characters. The target word is apt, and we'll demonstrate how the algorithm finds this word in the grid. Starting at cell 0, 0, which contains the character A, we mark it as visited and move to the next character in the word. From here, we go to 0, 1, which contains B, and mark it as visited. Next, we move to 0, 2, which contains the first C, and mark it as well. Then, we move down to 1, 2, where the second C is located, and continue marking. From 1, 2, we move to 1, 1, which contains E, and then to 2, 1, which contains D. At this point, we've matched every character in the word, so we return true. This example highlights how the depth-first search systematically explores paths while adhering to the constraints of adjacency and no reuse of cells. It also demonstrates how backtracking restores cells for use in other potential paths. Finally, edge cases to consider include scenarios where the word length exceeds the grid size, grids with duplicate characters that might lead to multiple valid paths, and configurations where isolated characters make the word impossible to construct. Each of these is naturally handled by the algorithm's structure and early exit conditions. Here, we start by defining a class called solution and implementing the method exist, which will determine if the given word exists in the board. First, we calculate the number of rows and columns in the board. Then, we define a helper function called DFS, short for depth-first search. This function takes 3 parameters, the current row, the current column, and the index of the character we are currently matching in the word. The base case checks if the index equals the length of the word, meaning we've successfully matched all characters, and we return true. Next, we handle the boundary conditions by ensuring the row and column are within bounds and that the current cell matches the character at the given index in the word. If any of these conditions fail, we return false. To avoid revisiting the same cell, we temporarily mark it as visited by storing its value in a variable temp and replacing it with the hashtag symbol. Then, we explore all 4 possible directions down, up, right, and left by recursively calling the DFS function. If any of these calls return true, we know the word can be constructed, so we store this result in the found variable. Finally, we restore the cell's original value to ensure the board remains unmodified for other paths, and we return the result of found. Now, we iterate through each cell in the board using nested loops for rows and columns. For each cell, we check if its value matches the first character of the word. If it does, we invoke the DFS function starting from that cell with an initial index of 0. If the DFS function returns true, we immediately return true for the entire exist function, indicating that the word is present in the board. If no path is found after exploring all cells, we return false, meaning the word does not exist in the board. This approach ensures that we systematically check every possible starting point and every potential path to determine if the word can be formed. Here, we start with the implementation of the word search problem in Java. The main function, exist, takes a 2D character array, board, and a string, word, as its inputs. First, we determine the dimensions of the board by storing the number of rows and columns in rows and calls. Then, we iterate through each cell of the board using nested loops. For every cell, if the character matches the first character of the word, we initiate a depth-first search using the helper function DFS. If the DFS function returns true for any cell, it means the word exists in the grid, so we return true immediately. If no such path is found after checking all cells, the function ultimately returns false. Let's now examine the implementation of the DFS function, which is defined right below. The DFS function is a recursive helper method that performs the actual depth-first search. It first checks the base case. If the index has reached the length of the word, it means all characters have been successfully matched, so we return true. Next, we validate the current cell. If the cell is out of bounds or its character doesn't match the current character in the word, we return false. To avoid revisiting the same cell during this search path, we temporarily mark the current cell as visited by replacing its value with a special character, hashtag. Then, we attempt to explore all 4 possible directions, down, up, right, and left, by making recursive calls to DFS. If any of these recursive calls finds the word, we store the result in the found variable. Finally, we restore the original value of the cell to allow other paths to use it and return the value of found to indicate whether the word was located in the grid. Starting with example 1, we are given a 3x4 board and the word apt. The exist function first calculates the dimensions of the board, setting rows to 3 and calls to 4. It then begins iterating through each cell to find the starting point of the word. At 0, 0, the cell contains a, which matches the first letter of the word. This triggers the depth-first search, or DFS, function, starting with, equals 0, c equals 0, index equals 0. Here, the character matches, so the cell is temporarily marked as visited by replacing it with hashtag. From this point, the function explores all possible directions. Moving down to 1, 0, it finds B, matching the second letter of the word. The cell is again marked as visited. Continuing further down to 2, 0, it encounters C, matching the third letter. Finally, moving right to 2, 1, it finds E, which matches the fourth letter. Each step progresses successfully toward constructing the word. The depth-first search continues from 2, 1. Moving right to 2, 2, it encounters D, matching the fifth letter of the word. This cell is also marked as visited. Then, moving down to 1, 2, it finds C, matching the final letter of the word. At this point, the function has successfully matched all characters, with the index reaching the length of the word. The function returns true. Before exiting, the board is reverted to its original state by restoring the temporarily marked cells. The final result of true indicates that the word apt exists in the board. Now, let's look at another example where the word is not found. Here, the board remains the same, but the word is SEZ. In this second example, the exist function again initializes the board dimensions and begins searching for the word. The first match is found at 2, 1, where the cell contains S, the first letter of SEZ. The DFS function is called with equals 2, c equals 1, index equals 0, and successfully matches the first character. The cell is marked as visited. Now, the function explores all directions. Moving down to 3, 1, goes out of bounds, and moving up to 1, 1, finds a mismatch. However, moving right to 2, 2, successfully matches the second letter, E, and the cell is marked. From here, the function attempts to find the next E, but all directions lead to either mismatches or out-of-bounds indices. Specifically, moving left to 2, 0, results in a mismatch. After exhausting all possibilities from 2, 2, the function reverts the board and continues searching from other cells. Ultimately, no valid path is found for the word SEZ, and the function returns false, indicating that the word does not exist in the board. Now, let's consider a simpler case with a 2x2 board in the word B. The exist function initializes the dimensions of the board as rows equals 2 and calls equals 2 and begins the search. At 0, 1, the cell contains B, which matches the word. The DFS function is called with equals 0, c equals 1, index equals 0. Since the current character matches and the index immediately reaches the length of the word, the function concludes that the word is found. The result true is returned by the exist function. This demonstrates how even single-letter words can be identified efficiently using the same algorithm. With that, we've walked through 3 examples showcasing how the solution handles different scenarios, from successful matches to cases where the word cannot be found. The time complexity of this solution is n*4 to the power of L, where n represents the total number of cells in the board, and L is the length of the word we are searching for. First, we have the outer loop that iterates through each cell in the board. If the board has rows and columns, this traversal alone contributes O(n) to the time complexity. Next, for each cell, we perform a depth-first search, or DFS, to explore all possible paths that might match the word. Since there are up to 4 possible directions from each cell up, down, left, and right, the branching factor is 4. The DFS process can continue for up to L steps, where L is the length of the word, resulting in a worst-case scenario of 4 to the power of L recursive calls. When we combine the traversal of the board with the recursive exploration from each cell, the total time complexity becomes O(n*(4 to the power of L). This reflects how both the size of the board and the length of the word affect the efficiency of the solution. The space complexity of this solution is O(L), where L is the length of the word. This is primarily due to the recursive call stack used during the DFS process. Each recursive call corresponds to one step in the path being explored, and in the worst case, the depth of recursion equals the length of the word. Since each recursive call takes O(1) additional memory, the total space contribution from the call stack is O(L). Additionally, the board is modified in place during the search by temporarily marking visited cells with a placeholder like hashtag. These modifications are reverted after each DFS call, ensuring that no extra memory is used to store visited cells. Hence, the board itself does not add to the space complexity. When we account for both the recursive stack and the in-place modifications, the total space complexity remains O(L). When analyzing the best, average, and worst cases, we see different behaviors depending on how quickly the word is found. In the best case, the word is found early, which minimizes the number of recursive calls. For example, if the first cell fully matches the word, the DFS will execute only O(L) steps along that path. In the average case, the algorithm will need to explore several paths across the board, but it doesn't exhaustively check every possible path of length L. As a result, the complexity stays closer to O(n*(4 to the power of L) on average. Lastly, in the worst case, the algorithm checks all possible paths of length L starting from every cell in the board. This means the full O(n*(4 to the power of L) complexity is realized, which represents the most computationally expensive scenario. To better understand the efficiency of the current approach, we can compare it to a brute force method. A naive brute force solution would generate all possible paths within the board and check if any of them match the word. This would involve exploring all permutations of the board cells, leading to a time complexity of O(rows*calls(L), which grows exponentially with the size of the board and the word length. In contrast, the optimized DFS approach significantly reduces the number of paths explored by focusing only on valid paths that could potentially match the word. By limiting exploration in this way, the complexity is reduced to O(n*(4 to the power of L), which is far more efficient, especially for larger boards and longer words. This demonstrates how the current solution strikes a balance between thoroughness and computational efficiency. To solidify our understanding of the time complexity, let's break it down mathematically. First, the traversal of the board contributes O(n) as we iterate through each of the n cells exactly once. Next, within each cell, the DFS process explores up to 4 directions recursively, resulting in a branching factor of 4. The depth of this recursion can go up to L, the length of the word, which leads to O(4 to the power of L) recursive calls in the worst case. When we combine these two factors, the total time complexity is O(n*(4 to the power of L). In conclusion, this algorithm effectively balances the cost of board traversal and recursive exploration to achieve an efficient solution. However, it's worth noting that while the DFS calls grow exponentially with the word length, this approach is still significantly faster than brute force methods and remains practical for moderately sized inputs. The space complexity, as explained earlier, is O(L), making this solution both time and space efficient given the problem constraints. When tackling the word search problem, there are a few common mistakes to watch out for. First, not validating input thoroughly can lead to runtime errors. For example, if the grid is empty or the word to search for is an empty string, your code could fail unexpectedly. Always handle these edge cases explicitly before diving into your main logic. Another frequent issue arises during DFS, where incorrect direction handling can occur. This might mean failing to reset visited cells after backtracking or not properly checking grid boundaries, which can cause infinite loops or invalid paths. Using a dedicated visited matrix or temporarily modifying the grid are great ways to address these issues. Additionally, ignoring constraints, such as the maximum grid size or word length, can result in inefficient solutions. For instance, assuming a brute force approach will work for large grids can easily lead to a time limit exceeded error. Finally, revisiting the same cell multiple times within a single path is another pitfall. This often happens if you're not tracking the visited status of cells properly, leading to incorrect results or infinite recursion. Being mindful of these mistakes can save you significant debugging time. Another common challenge is misunderstanding problem variations. For example, some problems require finding all occurrences of a word, while others only need one valid occurrence. Misinterpreting this distinction can lead to unnecessarily overcomplicated solutions, so always clarify the requirements before coding. In interviews, clarity is key. A clean and efficient DFS or backtracking implementation is often valued more than overly complex optimizations. For larger grids, it's helpful to discuss strategies like pruning invalid paths early or even pre-computing useful information, such as a frequency map of letters in the grid. Additionally, interviewers may test your understanding of trade-offs between space and time complexity. For instance, you might use a visited matrix, which requires O(m*n) space, versus modifying the grid in place to save space at the cost of changing the input. Lastly, clear communication is essential. Explaining your thought process, especially when handling edge cases or adapting to problem variations, shows maturity in problem solving and can leave a strong impression. To deepen your understanding of the word search problem, it's helpful to explore related problems. Starting with LeetCode 79, the problem we're currently discussing, you can practice implementing DFS and handling edge cases. For a more advanced challenge, LeetCode 212, Word Search 2, adds complexity by requiring the use of a tree data structure to optimize word searches in a grid. This is a great opportunity to learn how tries can reduce redundant checks. LeetCode 200, Number of Islands, is another related problem that focuses on grid traversal using DFS, helping you refine your skills in managing grid boundaries and tracking visited cells. Finally, LeetCode 695, Max Area of Island, emphasizes finding connected components in a grid, further reinforcing DFS or BFS fundamentals. By exploring these problems, you'll gain a more comprehensive understanding of grid-based algorithms. Now let's examine some alternative approaches and their trade-offs for solving grid-based problems like word search. A brute force DFS approach is the most straightforward. It involves exploring all possible paths starting from every cell in the grid. While it's simple to implement, it's inefficient for larger inputs, with a time complexity of O(m × n × 4 to the power of k, where k is the word length. This method works well for small constraints but quickly becomes impractical as the grid size increases. To improve efficiency, you can use an optimized DFS with early pruning. This approach stops recursion as soon as it becomes clear that the remaining path cannot match the word. While this significantly improves runtime, it requires careful implementation to ensure no valid paths are missed. For more advanced scenarios, like those involving multiple words, a tree-based search is highly effective. By representing the word list in a tree, you can minimize redundant checks and streamline the search process. However, this comes at the cost of additional memory for the tree and increased implementation complexity. Lastly, iterative DFS or BFS replaces recursion with stacks or queues, providing better control over memory usage and avoiding recursion depth issues. However, this method can be harder to debug and requires careful management of direction exploration. Each of these approaches has its strengths and weaknesses, and the best choice often depends on the specific problem constraints and requirements. Great work! We've successfully solved the word search problem using a backtracking approach. Remember, mastering recursion and backtracking is key for solving grid-based problems efficiently. If you enjoyed this explanation, be sure to like and subscribe for more content like this. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!